All right. Let's talk about today's do now. So today's do now, I might actually do it this way, so that way it all scans nicely. All right. The question was, how do you determine which is the oxidation half and the reduction half in a galvanic cell? What do? We look at the standard reduction potential on my sheet. Which one's the reduction half then? The higher pair. So something we need to keep in mind, and I'm just going to repeat this and write some notes on it, because it's really, really crucial in order to pass. Actually, I'll show you guys the notes from last lesson. So from last lesson, we talked about the achieved requirements for the standard cell, the galvanic cell. A lot of it is the same from the electrolytic cell. So identifying, in this case, that this is a spontaneous reaction, identifying the cathode is reduction, the anode is oxidation, identifying the definitions of reduction, gain of electrons, or you can tell me the oxidation number has decreased, oxidation, loss of electrons, oxidation number has increased. So those things all stay the same. The last thing you then need to do, and this is going to be the tricky part for the achieved, is being able to unpack the question and process it. So with whatever ionic compounds I give you, it's very different to the electrolytic. So I'm going to give you in these examples, what did I have on the board? Zinc, 2+, and zinc, and then I gave you iron 2 and iron. So that's going to be the setup for your questions now, is that you're going to get metals, and with those metals you'll get their corresponding cation with them. Unlike electrolytic cells, we're not just going straight from ion to element. One of these guys is going to go ion to element, and the other one's going to go element to ion. Okay? So the one that's going from ion to element, that one's going from a positive charge to 0. So is that oxidation, reduction? So that one's the reduction reaction. If I'm going from element to ion, we're going from 0 to a positive. So that is my oxidation half. So that's how we're going to figure it out this time around. Okay? So what you guys need to do, and we discussed this in our do now, is we need to use our resource sheet and look for the standard reduction potential, our E value. Just like you guys did when you were doing that calculation. You need to find both items on that resource sheet, and you got to figure out which of the two is higher, and that decides oxidation and reduction. The way I like to remember, higher one is the reduction reaction. The way I remember it is that this is called the standard reduction potential. So we are ranking them based off of how strong of an oxidant it is. Good? All right, so if I looked and I saw zinc right here and I saw iron right here, iron is higher, so iron will be going the reduction reaction, for example. So this will be doing the reduction half. This is going to go forward. And then zinc will be doing the oxidation half. It will be going backwards. Remember, you should always have one forward and one backwards whenever you're doing your work. And that was our do now. Questions, concerns, comments? Are we good? Do you need another example or you're okay? All right. Let's go back to the example that I did on, when did I see you guys? Monday? Which looked at zinc and the copper. Now, in fact, with the zinc and the copper, you guys did this practically as well, if you remember. And I have mine that I left reacting over the last couple of days, just so you guys can actually see the changes that you won't see immediately. Let's go through and talk about what we need to do, though, to bring this answer now up to a merit. So I'm getting my blue pen. Remember, blue is for merit. Red was for achieved. when I find my red, and I'll go find my green. There we go. So processing, achieved. Now we're going to do the merit. All right. Again, same things I am looking for in order to get this guy up to a merit. Keep in mind, for those that haven't sat part 2 or haven't, because they're later, backtrack. For those that have not done their second attempt, keep in mind that for this internal, you need to get all the cells at the same grade for the overall grade. So if the first electrolytic cell you got wasn't achieved, then the max grade you can get overall isn't achieved. So both cells need to be at merit for an overall merit. Does that make sense? So if you are waiting to do your second attempt, or you haven't done your first attempt because you're a late arrival to the class, just keep that in mind, that all of the cells need to be at the same grade. Cool. So similar kind of things that we are looking for when it comes to our assessment. We're looking for oxidation numbers. We're also looking for, just trying to check this tag. We're also looking for observations and things like that. I'm just double checking what I had on my requirements. Okay, cool. So, first things first, let's start with the easy stuff, which is going through and doing our half equations and giving our specific details in our justification. So for my reduction reaction, I have what I've identified as copper going to the copper metal. If I want to change this and add to it to indicate that this is an equation, with my reduction, I'm going to be showing I added 2 electrons. Happy with that? Right, other thing I'm doing is now being specific. So it has gained 2 electrons. My oxidation number has decreased by 2 from positive 2 to 0. You go? All right, zinc on the other hand, when I'm looking at it, at this half equation, I have zinc metal going to the zinc ion, its oxidation, it has lost 2 electrons, so I'm showing those electrons being on the product side. So there's my half equation for zinc. Giving my details, it has lost 2 electrons, the oxidation number has increased by 2 from 0 to positive 2. So now I'm justifying it. We good so far? All right. What else did I want to do? So we have our half equations. The other thing that's new, or sorry, that's old, is doing your E cell calculation. So E cell calculation, remember, we take our reduction reaction and we subtract the oxidation. So my reduction reaction with the copper, was it reduction? What is oxidation? Yes. All right, look for my list for copper. It's 0.34. Subtract away the standard reduction potential for zinc. Huh? You're subtracting. Yeah, so zinc. So zinc we have negative 0.76, but do you see how I have a minus minus? So I'm going to actually add those 2 numbers together because the negatives cancel out. If you put it into a calculator, it'll recognize that you're trying to subtract. So you're trying to basically add. So 34 minus a negative 0.76, 1.1. Always. But you have to be mindful that sometimes you're subtracting a negative number. So just watch out, but it's always minus. Yeah. I'll write that note because you guys are like, meh. Always subtract. Okay? All right, so I get 1.1 volts. Now, something you should be mindful of when it comes to our galvanic cells, it will always be a positive number. If you have a negative number, you have done something wrong. Negative numbers are for the electrolytic, positive numbers are for the galvanic. Neil, is that a question, or are you just enjoying the fan? You're fanning it. You're enjoying the fan. Okay. Cool. So that's the other thing you need to do for the merit. The last thing we need to do for the merit is our observations. There are several observations that I'm looking for. There's basically a total of 4 observations you can make. You are making observations on the 2 electrodes and the 2 solutions. Okay? First thing I'll do is I'll start with the electrodes because those are easy. So when I'm looking at the zinc electrode, do you see how I have the zinc metal going to the zinc ion? And what's going to happen is that where the zinc metal is coming from is actually the electrode itself. So the electrode would start to degrade. So Zn electrode degrades to form Zn2+. And in fact, because I had this guy running for ages, oh, it's kind of gross. You can see, hopefully, I'll move my hand so you can actually read the writing. You see how much thinner it is down here versus up here? That's it degrading. Now there's some gunk on stuff on there, but I think that might just be ions and stuff. Actually, I think something happened. That looks like copper. Oh, I see. The copper solution made it over onto the other side because of the salt bridge. All right. When we are looking at this here, we have our copper electrode, and we see the copper ion is going to the copper metal. So opposite happens here. The electrode gets bigger. So copper electrode gains mass from Cu2+ reduction. And when I grab my copper electrode, can't really see it, it's not as obvious, but it does have more copper than it did before. If we wanted to, what we could do is we could actually weigh it before and after. Would be the accurate way to do it. Yeah, Isaiah.
So this is like everything that's on the reduction side just gets bigger.
Yeah. So you can just remember the reduction side gets bigger, the oxidation side gets smaller. Which makes sense because if I'm reducing an ion, it's going to make the metal. And the metal itself is what's making the electrode heavier. And with the oxidation, like, you are losing the metal to become the ion, so it's gonna get smaller. Cool? All right. Next thing to talk about is the solutions. Unfortunately, my solution's basically all evaporated, so we can't really look at that. So I'm just gonna have to tell you. What color is the copper 2 ion? Blue. If it's becoming the copper metal, do I have as much copper 2 ions? No. So what would the solution then go? Will it be as blue? No, it'll lose its blue color because we're losing the blue ion. So that would be my second observation from this half, and now we're talking solution observation. So the solution becomes paler blue from the loss of the copper 2. Paler blue. Yeah, because the Cu2 is the blue. Cool. All right. Zinc sulfate. I'm going to have an increase in the zinc ions. Would I observe any color changes in my solution? No. What color is the zinc ion? Colorless. So even though the concentration of zinc is increasing, we don't have any observable change because zinc is a colorless ion. So we'll write that down. Even though the Zn2+ Conc is increasing. There's no color change because Zn2 plus is colorless. Cool.
There's no
Color change because the zinc 2 ion is colorless. So you're recognizing that there is a concentration change, but there's no observable effect because the ion itself is colorless. That's going to be quite often because most of the ions on that list are colorless. They're not fun. Not many things have colors. Conc is concentration because I can't be bothered writing out concentration and I was running out of space. Yeah, there's not many interesting ones. Copper's the one interesting one. Iron's an interesting one. Most of them are pretty boring though. Yeah. All right. Questions, concerns, comments? Yeah. Yeah. I'll do the full balanced equation. Right now, this is 1, that's 1, so it's balanced. That's 1, that's 1, that's balanced. Only if it's unbalanced. Don't start sticking 2s for the sake of sticking around, like sticking in 2s. Right? Are we okay? Okay. So, this is now at a merit level answer. Are we ready for the excellence? And don't you guys hate it that you have to do so much work for the merit and then the excellence is like 2 things and it's stupid. All right. Excellence. So 2 things I need for the excellence. I'm just going to grab a new piece of paper because I realize I'm running out of space and I don't want to cram my page. So first thing I need for the excellence is my full equation. So I'm going to take my 2 half equations that I have. I personally like to line everybody. Actually, I might do that in blue so that way we remember that's merit requirements. So Zn2 plus 2 electrons, Cu2 plus 2 electrons, Cu. All right, so that is my 2 half equations. Remember, we need those for the merit. Now, treat it the same way that you would normally. In this case here, I am looking at my electrons and seeing if the number matches. If the number matches, you are done. If they don't match, we are then multiplying the half equation. So that way the electron number matches. In this case, we have 2 and 2, already matches. Those cancel out. Sorry, I should be switching to green. And then put it all together. Halfway to the excellence. Yay!
halfway.
Halfway, because you said the last thing is just you got to write a sentence. Also, it's really annoying me that that volt is not centered. I think the idea that I had was that I was going to put the volt number here. You don't need to. I think that was my idea, why I put the volts like on the side. No, you don't. I'm just showing you what my thought process was. All right. Yeah. All right. Let me tell you what your sentence is. So, in this case, there's several things you need to do for the excellence. So, first off, we still need to justify that since the E cell is positive, we know it's a spontaneous reaction. The added thing that we need to explain, though, is how do we know that we are taking the copper standard reduction potential and subtracting away the zinc. So the reason why is, so now we're justifying our E cell calculation. So first thing that you would say is that E cell is calculated by taking the higher, actually, do I want to say it? Hold on, I don't think I like that sentence. Nah. Sorry, don't like that sentence. Let me start over. All right. Here we go. The more positive E cell, which in this case is, what do we say? Copper? Yes, copper. At 0.34 volts will be the reduction reaction. Because it is the stronger oxidant. Oh, sorry, because it has a greater standard, it will be the reduction reaction because it has a, it will be the reduction reaction because it has a greater standard reduction potential, making it a stronger oxidant. Sorry, you guys, I'm making this really bad. So the more positive the E cell, which in this case is the copper, will be the reduction reaction because it has a greater standard reduction potential, making it the stronger oxidant. Yeah. And then the next thing I want is the E cell is positive. The calculated E cell is positive, and therefore spontaneous and releases how much energy? I am not having a good day. And releases, if you want, 1.1 volts of energy. Energy. So we're justifying our E cell. Okay? And that's now an excellence level answer. And like I said, keep in mind, you need to get both the electrolytic and the galvanic cell at the same grade. If you are aiming for excellence, you then also need to write a comparison paragraph to talk about the similarities and differences between electrolytic and galvanic. I won't talk about that today. I think I'll talk about it next week to give you guys a bit of a break and not an overload on the brain. But basically, you're just, like I said, comparing the two. Neil?
So the galvanic cell, is it like electrolytic get 2 tries?
Yeah. You got 2 tries again. And I'll take the better of the 2. Cool. All right. So the plan for today is I'll let you guys have the rest of the period to practice these questions. I do have some on the board, and they're on Google Classroom as well. Now you can write them up to the excellence level. But if you're not feeling confident, I would say just go through all those problems and do them at the achieve level first, because there's no point in running when you can't walk. The other thing I want to give you guys a heads up on is that I won't be here tomorrow. I'm going to be at a wedding. So you guys will have a study session for tomorrow's lesson. I'm happy to write up some more problems if you guys want to do, or you can just work on some other subjects. Cool. We will assess this at some point. Normally, if I was here tomorrow and I saw how you guys were feeling, we might assess it on the Monday, but since I'm not here tomorrow, Monday I will check in with you guys, and then we'll probably assess this on Thursday next week. I think you guys should probably be ready for it. Cool. Alrighty. Time's yours.